So in this video here, we're looking at part 10C, which is all about the Newton-Rhapson process. So this is a little bit different. Well, it is different to iteration, but you'll see some similarities with the diagrams. So it goes as follows. We've got this blue curve in front of us, and we can see that down here, we've got the roots. So what we're going to do is we're going to start with an approximation. Maybe we've done this from an earlier question where we're inspecting roots or something. So we're going to start from here and we're going to go up. But instead of drawing y equals x this time, we're going to do something a bit different. So we're going to go up and we're going to make a tangent. So we make a tangent up here and we follow it all the way down. And we get to x1. What do we do from here? We're going to repeat the same process. So we will go up now, and again, we will make another tangent. And can you see that we'd be getting quite close to that value there? So x2 is looking really pretty good. Okay, so you keep going up, making tangents is sort of the idea. Now, there is a formula. You're not expected to be able to prove that. This one is in the formula booklet. It's that one there. Okay, so that's a formula booklet. And what it does is it is essentially doing this process. Okay, so it's taking care of this for us. But we do still, again, need to be able to understand what's going on diagrammatically. So here's a quick animation, which hopefully it's going to play. Yeah, there we go. It started now. And it's just sort of showing you what's happening. Value, curve, tangent, new value. Value, curve, tangent, new value, and so on and so on. So right near the start of the chapter, we talked about x equals cos x, for example. And let's say that we're going to start with an initial guess of 0.5. We would be using radians here because we've got some, what have we got here? We've got some differentiation going to be going on in this formula. So let me just show you the first one so you can get an idea of what's going to happen. Okay, so x equals cos x. We talked before about the idea that you can draw two different graphs and so on. But when we are using the Newton-Rhapson process, notice we have to set it equal to 0. So that's the first thing to notice. That's quite important. So we've written it as x minus cos x. Then the pieces of our formula that we need f of x, which we have here. And then we also need its derivative. So you can expect to do some fairly challenging differentiation in this kind of question. But for now, it's just minus sign goes to cos. Our formula, what was our formula? Our formula in general is that the next approximation is the one before minus the function evaluated at that point over the derivative evaluated at that point. Okay, so things to pay attention to would be like how x appears twice, because x appears twice in this rule. So we need a 0.5, a 0.5, a 0.5, a 0.5. Look how many 0.5s there are in here. We also want to show that we're substituting it in for our method marks. Okay, and again, we must be in radians in our calculator. So when we do that, we've got some approximations. 0.755, can't quite see that one there. 0.7, do you see it looks like it's converging? It looks pretty stable. So underneath here, a quick bit of practice. What would our different Newton-Rhapson process formulas be for this one here? Well, the top one, can you see that you've got x cubed minus 2, x cubed minus 2. The derivative is 3x squared. The minus 2 is gone. And you've always got this bit at the front. How about tan? So tan generally differentiates into sec squared. So personally, I would leave it like this unless there was any particular reason why I should write it a different way. That would be a show that though, so I would just leave it like this most of the time. And again, we would need to carefully sub in here. When you have sec squared, so practically just in terms of how you would type this one in, for example, xn is not a problem, minus tan x. So sec is cos. So this would be the same as then doing cos x and then putting that in as squared, okay? So I feel like that one's not obvious at all, but that's how you would do that bit. And the one underneath, you know, same again, okay? 2x squared minus 1 in the denominator, yeah? Something like this. Okay, so pause and have a quick go using the Newton-Rhapson formula with this question here, and we're doing just part C only. So hopefully you found that it wasn't too bad at all getting that result. Why beta rather than alpha? So remember we said before that roots, you tend to call the first root that you're talking about in a question, or the one most on the left, alpha, and then beta, and then if there's more, gamma, delta, etc. Okay, so my guess in this particular question why they use beta is because alpha is part of question A or B or something like that. And then just one more for you to have a go at. Okay, so again, xn plus 1 equals xn minus f of x over f dash x of that n. So what would we be doing here? We would essentially be doing 1.4 minus, and you would, let's put it in a different color, you would write all of this here with a 1.4 in the brackets squared. Okay, and then underneath, well, let's just do some work on the side. So f dash x, it's going to be 6x. What's that? That's 11x minus 2, so that's plus 22x to the minus, x to the minus 1. Is that right? Hang on a minute, what am I doing? Why is that 22? My brain switched off a little bit there, sorry. Plus 11x. Oh no, I am different. Yeah, I am differentiating. So what was I just saying? I just said plus 22x to the minus 3, didn't I? Yeah. Okay, so I would have that underneath as well. 1.4 plus 22. Hopefully you kind of get the idea. Over 1.4 cubed. All right, once you do all of that, you should get this answer here. Other things to be aware of, you just need to have a little bit of understanding about when the Newton-Rhapson process can fail. So if you want to understand how it fails, think about how it works. What it does is it goes up, it makes tangents, okay, and then it goes up, and it makes tangents and so on. That's how it works. It's not going to do anything here because it doesn't have any roots, and it's about trying to find roots, so it's not going to be very helpful here. Alternatively, what they seem to be talking about, something slightly different. Another problem that you would have is you have a division, right? So anytime you have a division by 0, this is not okay. So if the thing that you differentiate to when you sub in the number has 0, that's going to be a problem. So if you had minus cos, for example, which becomes sine, when you put a 0 in, that's going to be a problem, isn't it? So you could just use a different value, maybe, instead of a 0. Other things here, so this one is an unusual shape, okay? It is possible to draw curves in certain ways where they just never zero in, and you can see that here. Look at this gap, then that gap, then that gap. It seems to be getting further and further away from the root. Okay, so that should take you to the end of 10C. So that's the Newton-Rhapson process. We need to know the formula, be able to use the formula and show clearly that we're working. And we've just talked about some ideas as well about how, what would we say, about how if you're dividing by 0, that's a classic, or just based on the nature of some of the functions, it is possible that it will not zero in on the value.